the clicker. Hello, my name is Jesse Rocky, and today I will be presenting alongside John Armour, Errol Barshin, Nicole Finley, and Robert Long. We are the IDX Mass Timber Research Group at Washington State University. And if you've been following along with our videos so far, you'll have seen some of our analysis and development of the pilot supply chain for cross-laminated timber in the Pacific Northwest, as well as some of our early baseline building models for potential markets in the region. Today we'll be taking a close look at these buildings, but first I'd like to recap some of the processes that led us up to this point. This graphic represents some of the very early data we got in the first weeks of our research. We have basically raw geospatial data of some of the markets we had available. In the blue, some of the harvest and our resources. In the green, obviously the forest cover, and then everything in between. The mills, the manufacturers, roads and railroads. It was kind of a lot of information. We sifted through it and kind of narrowed our focus on something more manageable. Here's an example of that. Some more recent research and analysis that we did on four specific supply chains. On your left, you'll see one of the routes we chose. I believe it's from Forks, Washington, and that led to the number 3 on the map there, which is this zoomed in kind of aerial photo of the South Lake Union area where we decided to have all these routes meet. Now this is what we're studying currently as the South Lake Union area, but the important thing to note is that because we were able to focus on just these few specific instances, we were able to get a lot more out of our research. And the same thing can be said for our building models. So these are pretty much all the models that we've examined so far in our research. We have some warehouse on the end there, multifamily in various sizes, and office in various heights. This is what we have now. We narrowed it down and got rid of the warehouses in the 240-foot office for a number of reasons. One of the reasons is that we can focus on simply just our residential and the commercial, and because these heights are very similar and the buildings are very similar, we can kind of help each other research, but still have that individual learning and creativity that we can each have with our own model. One other important thing to note is that all of these building models fall into what is sometimes called a mid-rise gap, and the issue with this region right now is that traditional light frame timber can only be constructed so high before it becomes unsafe, about to that 85 feet, and then concrete and steel, which is far more expensive, is only really economically sound if you're building in very tall towers, so above this 160 foot here, or the 240 even. So this region here is something that developers aren't really interested in until now, because we have mass timber. We can get these buildings up quick and for cheap, and that's a really big opportunity for us to look into. And so here's a graphic from one of our previous presentations. You may have seen it already. It's for the multifamily buildings in Seattle since 1980, and we have all the different building types right here, all the materials they're made out of. You'll notice that the wood buildings are only up until 8 stories and nothing else really. The steel, concrete, and even the masonry is up here in these higher regions, but there's really nothing right above that timber, and that's the zone that we're kind of looking for. By the way, this is the multifamily residential map, and the office map that we also have, the office graph I should say, is very similar, so it's a good example of that. As for our locations, we started off with the 4-state region is what we called it, and that's Washington, Montana, Idaho, and Oregon. Last year we narrowed it down to the Puget Sound area. We had a lot of our current models in that area, as well as the warehouses fell into that category. We narrowed that down even further. Earlier this year even, we looked at some very specific possibilities in Redmond and Bellevue, but we decided to stick with Seattle because we were more familiar with the code. Although it's important to note that the code is very similar to Redmond and Bellevue, and a lot of our models can be very easily adjusted to fit those codes as well, so that's a great benefit for us for our models. So we're going to be focusing on the South Lake Union region specifically, and this is an urban center much like Northgate or the University District or Capitol Hill, and these areas are booming, a lot of population growth and a lot of buildings going up as quick as possible. So these are very good places for us to be designing for. And specifically these SM zones that you're seeing on this map are called Seattle Mixed Use. And in those regions we can actually build office or commercial and residential on the same lot. So that's extremely beneficial to us in that we can maybe even use multiple models of ours. And then here is a kind of zoomed in view of the same zones and where each of our building designs fall into those zones. So you can see that we clearly have a lot of options here, which is very exciting. However, building height and zoning are just two of many factors that we need to consider. So I'm going to go ahead and let Errol jump in here and explain some of our building assumptions, and he's going to show us some of the building materials that we could potentially use. So he's going to jump in here for that.
Hello. So the Seattle Building Code has several types of construction that are mentioned. Most of these are adapted from the International Building Code. And two pictured here off to the side are Type 1B and Type 3B construction. Type 1B is more typical in high-rise buildings. It's characterized by combustible or resistive materials, so stuff like concrete and steel traditionally. However, as we will show later, we are pushing for CLT to possibly be added to an acceptable material for that building type. And then also we have Type 3B construction. This is more common for low-rise buildings. It is characterized by a protected exterior from fire, and then on the interior you are allowed to have more exposed wood and combustible materials. Here we have Type 4 and Type 5A construction. Type 4 is heavy timber. So all the members in the structural system are oversized to allow for charring to occur, and so that it burns in a more predictable manner, and it has been shown that this performs a lot better than lighter members in fire, as might be expected. Then we also have Type 5A. This is protected wood frame. Currently this is dominated by stick frame construction. However, CLT would certainly be an acceptable material for this, but to make CLT competitive, we're looking to perhaps get an added height allowed by the building code. So then to kind of bring it all together, here's a chart showing all the different restrictions. As you can notice, there are restrictions for the exterior resistance to fire on all of these different building types. Once again, I'd like to mention that there are more building types than just these. These are the ones we need you to be familiar with for our presentation, because we are building buildings with these building types in mind. So now I'll go into some more of the assumptions that we're making for our buildings and some variances that we need to make them able to be constructed to code. So the first one is Type 1B. This is the tallest at 160 feet. You can see off to the side the office and multifamily buildings that we have for this. And here we're looking for a material variance. So currently CLT is not allowed for Type 1B construction. However, there is research being done that is showing that CLT is fire resistive, so it does not ignite readily just because it's so massive. It's kind of like the idea of a campfire or something. You need smaller stuff to ignite before you can get a large log to ignite. CLT is much the same way. And then we'll move on to Type 3B. So this is the one building that can currently be constructed to code as of right now. So this is a good one for us to compare the other buildings to. The reason this one can be constructed to code is because the inside is not restricted. However, the exterior needs to have a fire rating on it, which we are providing, as will be mentioned later, with our envelope. This is Type 4. This is the heavy timber, in case you didn't remember, so all the members need to be oversized. Now this governs also what CLT thicknesses we need and all the different layers, columns, beams, all those things need to be oversized to meet the code. However, the restriction that we need to be relaxed in order for this to work is the height restriction. So this building, as designed, is currently 125 feet and 10 stories, which traditionally is not that far off. However, current codes do not allow that, but based on precedent, and current changes that are being looked at in the Canadian codes, we're thinking we can make a good argument for CLT buildings to go up higher than that current 85-foot restriction. And then lastly, we have a type 5A building. This building, we are trying to argue that a building that is designed to the current 65-foot limit, note this is for the tower only, with the podium, I don't want to get too confusing here, but with the podium it can actually go up higher. But currently the 60-foot restriction on the wood portion of the building, we're arguing if that would be relaxed, it would be structurally equivalent, because at 60 feet the wood members and components are not fully stressed and their structural capacity is not fully utilized. So now I'd like to hand it off to Nicole, and she will talk a little bit about floor plans.
So as Errol and Jesse have both discussed, the zoning, location, and building type of our buildings plays a role in how we plan to lay them out and or design them. Behind me you can see the 5 buildings we will be exploring. Starting at the right, we have a Type 1B office, a Type 3B office, a Type 1B multifamily, a Type 4 multifamily, and a Type 5A multifamily building. The biggest difference you can see between these buildings is their general size of their floor plans. This is the biggest variety we see, and a lot of this is limited by the type of the building and or the zoning of the building. The other variable you see is the general layout of the buildings. The office target more open space, while the multifamily buildings are target specific markets for unit size and are attempting to maximize the amount of occupants they can have. Seen here are the 2 office buildings, and as you can see with their floor plans, they are very similar. They will use a shear core system to transmit lateral loading, and will use a gravity system of columns and beams. If we take a closer look at that larger building, we can see that it does feature these shear walls, the beam column system, and it also features these cutouts on the side that allow the building to fit into those area limitations. This building features a 24-foot span that is achieved through a 5-ply CLT panel, along with composite action between that and the concrete topping. If we take a look at the smaller office, we again see a very similar floor plan. Again, it's going to use those shear cores and that beam column system to resist gravity load. And then as you can see here, we again have that 24-foot span, which also requires composite action between the concrete topping and the 5-ply CLT panel. If we look in here, we can see the difference between the sections of the building. So on the bottom, you will see the plan view for the 2 offices, and then above is their corresponding section. Again, the biggest thing you'll notice right away is just the size of these buildings. Again, that Type 1B building is going up higher than that Type 3B building. The biggest difference you'll notice is from the podium, the concrete columns that extend up into the CLT tower must extend further up in the 160-foot tall building. This is due to the compiled loading of the above floors down to that base. If we move into the multifamily, we can see again that we have very similar layouts between these buildings. These buildings will use a distributed shear wall system to transmit lateral loading, and they'll be using a bearing wall system to transmit gravity loading. As you can see, the layout's very similar. Your biggest difference is going to be in size. However, another difference is going to be in just unit size. The Type 4 building and the Type 1B building target markets of 1 to 2 bedroom apartments, where the 5A building is going to target a studio to 1 bedroom apartment. So if we take a look at that taller multifamily building, we again see that 24-foot span, and it, like the office, is achieved through a 5-ply CLT panel and a composite action between that and the concrete topping. This building also features a double 5-ply CLT wall for its interior wall system. This would consist of a 5-ply wall, some sort of insulation or air, and then another 5-ply wall sandwiched around that insulation. There are many ways to achieve the routing for mechanical, plumbing, and electrical. However, we've decided to go forward by routing our electrical through these walls in order to access all the units. Moving on to the Type 4 building, we see a unique characteristic here. The 24 span is again achieved, however this time we use purlin spanning from the 2 interior walls. The 5-ply CLT panel is actually oriented parallel to the interior walls. There is a concrete topping, however composite action is not needed between these elements to achieve the 24-foot span thanks to the purlins. Again, we're going to see that double interior wall. It's going to be a 3-ply CLT wall instead of a 5-ply CLT wall. Finally, we have that smaller multifamily building. This building features a unique 16-foot span, And it also uses a 5-ply CLT panel to span this distance. There is concrete topping, but again, composite action is not needed to reach that 16-foot span. This building uses a double 3-ply CLT wall, again for the interior. However, the exterior walls and hallway walls feature just a single 3-ply panel and extra insulation to either route mechanical, plumbing, or protect the interior from elements. There will also likely be an interior partition wall that will be put in each unit to allow plumbing to each of the units. Taking a final look at the assemblies of the multifamily buildings, we see here on the bottom level is the floor plan for the individual units of each of these buildings. They have various loadings per floor between the 3 buildings. Then looking above that, we see the section for these units for the first 4 floors of CLT construction. As you can see, they align with the walls, and you can understand how tributary area would come down through these buildings. Also, you can notice that for the Type 4 and the Type 5A, the bottom floors consist of that 3-ply double wall all the way down. However, with that Type 1B building, you're going to see those 3-ply double walls transition into a 5-ply double wall to take care of the extra loads from the above floors. And now I'd like to hand it over to Rob, who will go into more detail on the connections and details of these buildings.
All right, thank you, Nikki. So up until this point, we've really been focusing on the bigger scheme of things. We've been looking at floor plans, we've been looking at elevations, what type of material we're going to be using, all really important aspects to look at in our building design. But now I want to look at a detailed look of the connections that we're going to be using. I've heard it said that a building's made of connections with a lot of material just in between those connections. And it's really important for our building because it's really what pieces our building together. To set it up, I want to first convey to you guys that these are just preliminary designs. These haven't been engineered. These haven't been sized appropriately. So the reason why we do this is because we first need to see what the layout of these connections are going to be according to IBC. There's different codes that we have to adhere to according to the different building types. And so because of that, we want to make sure that we have our layout correct, and we have a visual analysis of that, and then from there we can go in and we can actually start sizing out what size steel we need, what size bolts we have. So this is all preliminary. This is a visual effect that we need to go through first in order to move forward in designing the size of steel and the size of bolts. Also, before I get into this, I want to convey that for each building type, what we've done is we've used balloon type construction. And so what balloon type construction is when the diaphragm comes and it ties directly in and hangs off of the wall or column. And this is opposed to platform construction where the diaphragm would sit on top of the wall or on top of the column, and then the next wall or column would be placed on top of that. We're not doing that, and primarily because we want to avoid issues of shrinking or swelling. Even crushing for the top or for the larger buildings could happen and occur in the diaphragms. And so to avoid all that, we're doing balloon construction. You'll see it in the slides to follow. So starting first with our Type 5 multifamily resident unit, as you can see here, we have a bearing wall system. The walls come and connect together from steel plates, connected then by bolts. As Nicole had said, was that there's a micro wool inside of there's a micro wool that is sandwiched inside of the 2 CLT panels. For this one right here, we have 2 3-ply CLT panels, and then inside that is the micro wool. And within the micro wool, you can run the conduit, you can run electrical, whatever it is that you need, you have that space there. So we're using either 3-ply CLT or 5-ply CLT on either side to sandwich those together. As you can see here, that the CLT diaphragm comes and it hangs directly on a hanger. It's just a L-shaped bracket made of steel, and this is attached to the steel that's attaching the 2 walls together. And it just hangs directly on that. We have the concrete on top, as well as insulation. We have gypsum board on either side for fire protection. And then furthermore, to connect these diaphragms together, we're going to notch a little bit out of that CLT. We're going to place some steel plates in there and then bolt it together, and we should be good to go. Next up is we have the Type 3B office. What's important about this to note is that this is not a CLT wall, however it is a glulam beam, or a glulam column, excuse me. And so the glulam columns are stacked on top of each other. We did think about doing just 60-foot columns, but the problem is the constructability. And we found that it'd be probably a little bit easier for us to construct this, doing it in segments where they're bearing on top of each other, and we decided to go with that instead. And so you see this this H bracket, I like to call it, of steel, where they both slide into each other, and bolts are then connecting them together. And then from that bracket right there, you can see there's a curve plate. And on this curve plate is how what we have here is a glulam beam coming and attaching right into that column. And so what we do is we're going to notch out the glulam beam. It's going to slide right into the curve plate, pop a bolt in there, we're going to be good to go. And that goes from one column, the glulam beam then goes to the next column. Then orthogonal going into the page is going to be our CLT panels that are sitting on top of that, bolted in, and they're going to be spanning that 24 feet with the concrete on top, which we need for the composite action. And then furthermore, to connect the columns down into the foundation, we're going to be using some sort of anchor bolt system to make sure that we have a sturdy connection there. Next up is we have the type 4 multifamily residence. And so what you're going to notice about this is that there are some similarities between the office that we just looked at. However, that this building is going to have a CLT wall instead of a glulam column. So that's kind of the difference here. The same sort of ordeal. There's going to be a metal sheet there, a metal bracket that connects the two walls together. And then from that, there's going to be a glulam beam that comes and attaches into the wall itself via a curve plate. Same exact thing. Take a notch out, put it in, then a bolt, and then you're good to go. That spans between each CLT wall. And then from there, the same exact thing, the CLT is going to sit on top of the glulam beam, and it's going to span the 24 feet. And then furthermore, to connect those diaphragms is going to be a very similar idea of bringing them and splicing them together, of which we've already shown. Now we're going to be getting into the type 1B construction. And the big goal with this and the biggest challenge was overcoming the fire issue. And what I mean by that is all the connection had to be completely covered. There couldn't be any connection without some sort of gypsum board or something covering over it where no steel is actually showing. So that was the biggest challenge for this. As you can see for the type 1B multifamily house, is that you have two bearing CLT walls connected and spliced together from two steel plates, bolted them together. And what I have here is there's a hidden bracket, or there's a bracket coming off of the wall with a hidden bracket submerged into the diaphragm itself, and those will come and meet up together and be bolted together. Once you put gypsum board underneath that, it should be completely covered. And also furthermore, if there's any bit of gap that might be in between the wall and the diaphragm, there's actually a foam that that meets code to completely cover that if there happens to be any of that showing. So that's kind of a backup plan in case if we need to utilize that. Same thing, connecting those diaphragms together is a splice plate, but this time we're using a male-female connection, and that's going to slide right in together with steel plates on either side, bolt that together, and good to go. And last here we have is type 1B office. What you're going to notice here, that's the main difference, is the concrete column. This goes up from the first story up until maybe the fifth story or so. We haven't completely figured out how high we need to have these concrete columns go. But from these concrete columns going into the page, we're going to have glulam beams that are attached to the column itself. Then from that, that's going to be used as a ledger where the CLT panels or the CLT diaphragms, are going to come and rest right on top of that. And then again, making sure all these connections are covered and everything is a huge important factor for this. And with what we have here, everything seems to be good. And so it's going to be further details as we go into the design of how exactly these are going to work. And then lastly, the diaphragm is going to be the same thing, male-female piece connected together. And so thank you for hearing this portion of the details section. Last, I'm going to invite John to come up, and he's going to talk to you about the envelopes and then the next steps that we're going to be taking in our research.
So one of the other things we've been researching this semester is we've been taking a look at building envelopes. And really what a building envelope's job is to keep the exterior environment of the structure, or of the environment, out from the interior of the building. And whether that be snow, rain, wind, water, and heat, extreme colds, extreme temperatures. And kind of the systems that we've come up with for our 5 baseline models is we want to use a curtain wall system for 4 of our models and a window wall system for 1 of our models, and that one model is the 85-foot multifamily structure. And the big difference between a curtain wall system and a window wall system is that curtain wall is one continuous sheet of glass, and window walls are broken up between floor levels. So they attach to the bottom and the top of each floor, while curtain walls attach to the side of the floor. And kind of some of the negatives and drawbacks and positives of each of these is that the curtain walls are about 4 times more expensive than window walls, but and they're usually on high-end structures, but they are extremely good at keeping out moisture because there's no gaps in between the structure. Whereas window walls have a tendency to leak if they're not quite installed right because there's so many more gaps within the structures they have to connect to the bottom and top of every floor. But window walls are about 4 times cheaper than curtain walls, and they also offer a better noise insulation between the structure because curtain walls are one continuous wall. They have a tendency to let noise travel between the floors. So you might be able to hear something on the 3rd floor if you're on the 2nd floor. And that's kind of some of the main drawbacks and differences between window walls and the curtain wall systems. Getting into the details of how we might connect these to our structure. Here we have the curtain wall set up, and you can see that our structure is connected to the outside of the floor. We wanted to make sure that we were connecting into the diaphragm of our structure. So we had a steel plate that connects to the mullion, and then the mullion connects to the window. And so if wind was to hit this structure, it would, half of the wind load from the bottom half and half from the top half would then be transferred directly into the floor diaphragm. And as we've talked, this is exactly how we want to deal with that lateral load because CLT is really good in in-plane shear. And then for our window wall system, we wanted to connect this by, and this kind of shows a good example of how the window wall and curtain wall are different because this shows how the window wall is inside the structure whereas the curtain wall is just barely outside the structure. With this, we're connecting to the bottom of the floor, or of the ceiling above, and to the top of the cribble wall below it. And then with this, half of the load that would hit the window would get transferred to the floor above, and half of the load would then go down to the cribble wall below. And that cribble wall would act as a beam, transferring that load directly into the floor diaphragm below. That would happen on every floor. So moving kind of forward to our next steps, we wanted to start taking a look at what kind of environmental impact would happen based on the different building envelopes we've chosen. So with our 85-foot multifamily, the one that's different, the window wall system, there's going to be a lot of walls on the structure, and so we're going to take a look at what kind of R values we can get with the insulation that we're going to use with those walls. So as you can see in this kind of exploded view, on the left side there's the gypsum board, then the rigid insulation, then our CLT panel, and then an exterior barrier siding that's also going to have some kind of moisture barrier to keep the CLT from getting wet. But we want to take a look at how well we can insulate the structure and kind of keep it energy efficient. And then we also want to take a look at our window wall or curtain wall systems that the other 4 building models are going to have, and what kind of glass we're going to use, what kind of R values we can get out of the glass, if the glass is going to be tinted or not, and how that's going to affect the structure. Another aspect that we're looking at as we move forward is we're looking at the seismic analysis of our structures. And so right now we're looking at 3 different main lateral force resisting systems. We're looking at lateral bracing, we're looking at CLT walls as shear walls, and we're looking at concrete shear cords. Based on what lateral force resisting system we use, it's going to give the building a different ductility, which will then in turn give the building different design loads for each floor and seismic. And so we're going to take a look at how each one of these different lateral force resisting systems affect our building, and then in turn we're going to make a decision as to how we want each one of these buildings to perform based on our choice of which system we're going to use for the building. And kind of our end result here is we want to create structural drawings for each one of our 5 baseline buildings. And we've seen some of the details, some of the floor plans. We're already on our way, but we want to wrap it up so we have professional structural drawings for each one of our 5 building types. And that's kind of our end goal of the semester here. And that kind of concludes our presentation. If you have any questions or comments, we'd love to hear from you. Thank you for your time, and this is a list of what we all presented on, so if you would like to address us directly or as a group, either is great. Thank you.